Hello students, welcome back. The next topic is Wilson's theorem, section 2. Here's Wilson's theorem. If p is prime, p minus 1 factorial is congruent to p minus 1, or equivalently speaking, negative 1 modulo p. Now if you flip this negative 1 to the other side, you can re-express the same thing like this. P minus 1 factorial plus 1 is congruent to 0, and this expression is also widely used. Another expression that is equivalent to the original is this one here. The equivalence between these two, well, it is a matter of flipping one to the other side, one way or the other, so that's easy to see. How about this one? This versus that. Is that easy to see? Well, let me give you a hint. I'm going to leave the detail to students. P minus 1 factorial is, by definition, P minus 1, P minus 2, P minus 3, and so on and so forth, all the way up to 1. So we can rewrite it as P minus 1 times P minus 2 factorial. Do you see that? P minus 2, P minus 3, P minus 4, all the way up to 1. That's same as P minus 2 factorial. So we can rewrite like this in general. And this is not congruence, this is equality. Now plug this into here. And then, okay, all right, I'm giving away a bit too much. Use this hint to prove the equivalence between the original and the third expression here. It's not going to be too hard. Now, in terms of application, this is the most useful. And this one, okay, almost equally as useful. And everybody can see that they are equivalent immediately. And as for this one, it's not very useful in terms of application, but we're going to use that for the proof. So for the proof, the third expression is useful. For application, it is not. Okay, let's go ahead and prove it. First, let's go ahead and take care of some trivial cases. Two trivial cases. When p is 2 and p is 3, we have this and that. All good? Alright, trivial cases, they all work out. Therefore, let us assume from this point on, the prime number p is greater than 3. In other words, p is either 5, 7, 11, 13, and so on and so forth. And based upon that, let's make this claim. P minus 1 factorial, which can be decomposed like this, turns out to be congruent to this. Let's see. P minus 1 does not go anywhere. It stays as P minus 1. Or I could have rewritten as negative 1. That's fine too. And 1 doesn't go anywhere either. So 1 is 1. Okay. The key point is the middle part, which I'm highlighting in red. We have a bunch of 1s only. Why is that? Let's consider the multiplicative inverse. The multiplicative inverse of 1 is 1 because 1 is the multiplicative identity. How about that of p minus 1? That is itself as well. This is congruent to negative 1. So negative 1 times negative 1 is positive 1. So yes, blue, blue, green, green, those are taken. How about all other multiplicative inverses? They all have multiplicative inverses uniquely, distinct from itself, and they all have to come from here. And then there are even number of factors here, so we can pair them up. First number times its inverse, second number times its inverse, third number times its inverse, like that. We have a bunch of 1s. Let us elaborate that idea. So let's make this observation. Multiplicative inverse exists uniquely as, because p is prime, as long as a is non-zero. And then we can make this kind of classification. A is either 1, green, or a is p minus 1, blue. Otherwise, 2 to p minus 2, they're all red, the middle part. And then outside the bracket, If A is congruent to 1, then A inverse is 1, that's green. And A is P minus 1, then A inverse is also P minus 1, or equivalently speaking, negative 1, that's blue. As for everything else, is the red part. We have the inverse, and then change of order because multiplication is commutative, so we can pair up inverse, inverse, like these, and you have a bunch of ones. As a result, we get p minus 2 factorial is congruent to 1. You see, we multiply p minus 2, p minus 3 all the way up to 2, and then multiply 1 will not change anything, so we have p minus 2 factorial, and that's congruent to 1. That completes the proof of Wilson's theorem. Yeah, this completes the proof of Wilson's theorem. Okay. That's that. And then let's consider an application problem. And I have an application problem here, but it's interesting, but it's pretty tough. So I'm a little bit torn between what to do. Shall I just go ahead and cover it like a normal topic, or shall I consider it as an exceptionally hard optional topic? For now, let's consider it as a normal topic, the usual topic, and maybe later I may make some other decision, but more can always replace less. Therefore, for now, let's just zoom everything in. Let's count everything in. Okay, here's a problem. P is an odd prime. Then a quadratic congruence, x squared plus 1 is congruent to 0 mod P has a solution if and only if P is congruent to 1 mod 4. Okay, this says congruence mod P, but how in the world this mod 4 suddenly came out of nowhere? Well, it didn't really come out of nowhere. It's just a typical way to classify odd primes. P is an odd prime, so there are two types of odd prime. P is congruent to 1 mod 4, and P is congruent to 3 mod 4. You see, if I divide any integer by 4, then that integer can be written as 4k plus 0, remainder is 0, but this is composite. Four k plus 1, that's an odd integer. And then 4k plus 2, that's an even integer. And then finally 4k plus 3, that's an odd integer. Now, as for prime number, there's no chance I'm going to get a prime number here. Everything here is composite. It's a multiple of 4. So that's out. And okay, that's a candidate. That's a good one. And that's the case that we are going to consider. And how about prime numbers that fall into this? There's exactly one such prime number. That is 2 when k value is 0. But the problem says we are dealing with odd primes, so that's out of consideration as well. P is 2, that's even prime. Finally, this one here, well, this example problem is telling you if this congruence has a solution, then we have to have this. Not the other way around. Not the other. Okay, that's how this mod 4 came out. It didn't come out as out of nowhere. It's just a normal way to classify odd primes. Alright, forward direction. Let's assume there is a solution. In other words, a squared plus 1 is congruent to 0, so that a squared is congruent to negative 1. And then let's prove P is congruent to 1 mod 4. What do you do here? We use Fermat's theorem. Let me highlight the first part in blue. 1 is a to the p minus 1 power. And then let's make this a bit ingenious manipulation. A squared and then divide 2 and the power. Let me expand this font so that you can read the powers better. Now, is it possible? Yes, p minus 1 divided by 2 is an integer because p minus 1 is an even number. Remember, p is an odd prime, so p minus 1 is even, so p minus 1 divided by 2, that's an integer, so this is valid expression. And then a squared is -1, so we get -1 to this p minus 1 over 2 power. All right, so 1 is -1 to some power. This had better be an even power. Otherwise, we're going to get -1, right? So that's has to be 2k, and that's it. Flip this denominator to the other side, we get p is 4k plus 1, and that's precisely what we wanted. Okay, we use Fermat's theorem, and then this p minus 1 divided by 2, that technique to prove it. Now let's consider the opposite direction, but this p minus 1 divided by 2, that shows up again. Okay, if p is congruent to 1 mod 4, then there's 4k plus 1 form, so p minus 1 is 4k, so p minus 1 divided by 2 is an even integer, is 2k. And then let's apply Wilson's theorem. P minus 1 factorial is congruent to -1. Now, let's pair up like this. P minus 1 versus 1, they add up to what? P, that's 0. P minus 2 and 2, they add up to P, which is 0. And then let's do one more. P minus 3, and then 3. Brown, brown. They add up to p, which is 0. So what conclusion can I draw? P minus 1 is -1. P minus 2 is -2. P minus 3 is -3. We can get all these kind of conclusions. And then right here, sorry about the typo. So these two add up to p, which is 0 as well. So this p plus 1 is negative of p minus 1 over 2. Same as before. So if I multiply them up, then p minus 1 times 1, so that is negative of 1 squared. P minus 2 times 2, that's negative of 2 squared. P minus 3 times 3, negative of 3 squared. And finally these two, negative of p minus 1 over 2 squared. So what do you get? We get this factorial squared. And then we have a bunch of negatives right there. So we get negative of, well, how many terms are there? 1, 2, 3, 4, up to p minus 1 over 2. Yes, p minus 1 over 2. There are that many negatives out there. But then again, p minus 1 divided by 2 is an even integer. So this thing here is congruent to 1. Because we established this. So what we have, this p minus 1 over 2 factorial, this thing here, squared is congruent to -1. Oh, we have a solution. If we put this a as p minus 1 over 2 factorial, then that's a solution of this quadratic congruence. So that completes this problem. The proofs in both directions. Fourth direction required Fermat's theorem. Second direction, the other direction required Wilson's theorem. Pretty tough, but I'd say it's beautiful. We're using two very, very famous theorems in a single problem. And the conclusion is interesting too.